So we have learned that best case running time of linear search is, what's the best case running time of linear search?
It's constant, we go of 1.
It's a constant, that is n power 0, order of growth is n power 0, that means it is constant. It is constant. What is worst case running time, order of growth of worst case running time of linear search?
It's n.
It's n power 1, that is n. N means it is linear in the size of input. Linear in the size of input. And we also, from the definitions, it is clear that T best of n less than or equal to average of n, T average of n less than or equal to T worst of n. So now, let us observe this. Okay. So I have given 60 statements here. Okay. First of all, you should tell me whether they are right or wrong. Worst case running time of linear search is big O of n. Is that correct? In the worst case, what is order of growth?
Yes, sir.
Order of growth is n square. So is this true? Similarly, worst case running time of linear search is big omega of n. Is that true?
Yes, sir.
Yes. The worst case running time of linear search is theta of n. Is that true?
Yes, sir.
Out of these three, out of first two three, which is your favorite?
Theta of n.
Theta of n. So theta of n is favorite answer. No, this is our favorite. No, this is our favorite. Now, okay, in the first statement, first three statements, remove worst case. Remove worst case. Then the statement is like this. No, running time of linear search is big O of n. Is it true or false? Fourth one, is it true or false?
That is true, sir.
Running time of linear search is big O of n. What about fifth one? Running time of linear search is big omega of n. Is that true or false?
That is also true.
Okay. So I elaborate on that. After that, you should tell me whether they are true or not. So whenever we say running time of algorithm, running time, if there are no cases, then it is only one running time. If at all there are cases, then we need to talk about, that means it says about best case also, it says about average case, it also says about worst case. That means if we write running time of algorithm is something means, then it should be true for worst case also, it should be true for average case also, it should be true for best case also. It should be true for best case also. Is that correct? If there are no cases, then there is no confusion. Only one running time will be there. Only one running time. If at all there are cases, we usually talk about best case, worst case, and average case. No, best case, worst case, and average case. That means running time of an algorithm is something means, it means it is saying three things. Best case running time of this algorithm is something. Average case running time of this algorithm is also the same thing. Worst case running time of this algorithm is also this same thing. Is that clear? Is that clear? Now you please tell me whether fifth statement is true or false. Fifth statement. In the best case, okay, I am talking about fifth statement. In the best case, what is order of growth? Order of growth is n power 0. We know that in the worst case, order of growth is n power 1. In the best case, what is order of growth of linear search? N power 0, that is constant. In the worst case, what is order of growth of linear search? In the worst case, what is order of growth of linear search? N power 1, no?
Yes.
Yeah, n power 1. Is that okay? Okay. Now, What can you say about its order of growth in average case? We don't know. We have not yet calculated this, but we can say that order of growth in this case is between n power 1 and n power 0. Can we say this? The average
Yes,
case
yeah.
order of, we don't know what is that. That later we'll actually calculate. Okay. Right now we can say that it is between these two, n power 0 to n power 1. Now read statement 5. That means what? It is actually saying three things. It is saying three things. One is, it says that best case running time of linear search is, okay, I use LS, linear search is big omega of n. It also says that, what is the other case? Worst case. Worst case running time of linear search is big omega of n. It also says that average case running time of linear search is big omega of n. Correct now? Whenever we say simply without explicitly saying whether it is best case, worst case, or average case, whenever we say running time means it should be true for best case also, worst case also, and average case also, no? Average case also. Is that clear? It should be true for all three cases whenever we use running time without explicitly saying whether it is best, worst, or average. Is that point clear?
Yes, sir.
Okay. Now you please check whether this best case running time of linear search is big omega of n. Is that true or not?
It is false, sir.
It is false.
Yes, it is false.
It is false. Why? Because we know that in this case order of growth is n power 0. Then we are saying n power 0 is big omega of n. Is that true? No. This side it should be more. No. Order of growth should be more than n. That means this statement is false. This statement is false. Worst case running time of linear search is big omega of n. Is that correct? Is that correct? Is that correct?
Yes, sir.
We have already discussed, no? So this is correct. Okay, anyhow, we have not discussed about average case. We are not going to talk about it for the moment. Okay. Now, that means it should be true for all. It should be true for all. But for one thing, it is automatically false, no? It is automatically false. It is false, no? Already for best, in best case, it is false, no? That means, can we say that running time of linear search is big omega of n? Is that correct or not? Is that correct or not?
No, sir. No, sir. It is.
No. That means, when does it become correct? For best case also it should be true, worst case also it should be true, average case also it should be true. Then only it becomes true, no? So from this we can say that this is wrong. Is there any doubt here?
No doubt, sir.
Okay. Now look at the sixth one. Look at sixth one. A running time of linear search is theta of n. That means, now I am talking about sixth one. That means it says that best case running time of linear search is theta of n. It also says that worst case running time of linear search is theta of n. It also says that average case running time of linear search is also theta of n. Now you tell me, among these three statements, 6 is correct. When does it become correct? If all three are correct, then 6 is, we can say that it is correct now. Now, best case running time of linear search is theta of n. Is this statement true or false? Best case running time of linear search is theta of n. Is it true or not?
It's false.
It's false, sir.
It is false. We know that in the best case, it is order of growth is how much? Order of growth is order of
One.
growth is n
N-
power 0.
N
But
raised
we
to
are
zero.
saying n power 0 is theta of n. No, this is not correct. Hence, it is false. Worst case running time of linear search is theta of n. Is it true or not?
True.
It is true. No. Worst case running this state for this it is correct. But there is one example where it is fail. It fails. No, for one case for which it fails. No. Hence, whether sixth statement is true or not. It is true or not. Whether sixth statement is true or not. Sixth statement is that true or not? Sixth statement, it is false. Have you understood? Because our case we have not discussed anyhow so far, but still without even knowing this, automatically we have got one false answer. No, without knowing that we have already got one false answer. No. So based on that, can you conclude that running time of linear search is theta of n is not correct? Is that correct? Running time of linear search is theta of n. Is that correct or not? Is that true or not?
It is false.
It is false. Why is it false?
It is failing in the case of best case running time.
In best case, it is false. Now look at fourth one. Look at fourth one and tell me. Look at fourth one.
It is true. It is
Now look at
best
fourth
case.
one. So best case running time. Okay, BC I write here. Best case RT running time of linear search is big O of n. Similarly, what is that? Worst case running time of linear search is big O of n. Average case running time of linear search is big O of n. Is this true or false? This statement, best case running time of linear search is big O of n. Is that true or not? Is that
It's true, sir.
True.
What is order of growth here? N power 0. N power 0, can we represent it as big O of n?
Yes, sir.
Yes, that's why this statement is true. Okay, worst case running time of linear search is big O of n. In the worst case, what is its order of growth?
Less
N
than
power
order
1.
of n.
N power 1 is big O of n. Is that true or not? N power 1 is big O of n. Is that true or not? In the what is worst case, in the worst case, what is its order of growth? In the worst case, we know that its order of growth is n power 1. No? That is n. So that means worst case, that n, is it possible to write it as that is, which is nothing but at what is that we are asking, is n is big O of n. Is it true or not? That's what we are asking. Is that true or not?
It's true. True, sir.
It is true. No, it is. Why? Because order of growth of this both are same. No, both are same. No, but that means big O notation definition. This side same is also allowed, or even less also is allowed on right left side. No. Now average case running time of linear search is big O of n. Is it true or not? Is it true or not? We only know this much about average case. It is between n power 0
True,
to
sir,
n power
true.
1.
Because it should be less than n, sir.
It is
True.
whatever it may be, it is not more than n. No, whatever it is not more than n. That means whatever value is here, is it big O of n or not? We know that it is from n power 0 to n power 1. We don't know exactly as of now. Is that correct or not? Is that correct or not?
Yes, sir.
N
Correct.
power
Correct, sir.
0 is big O of n. Is that correct or not? N power 0 is big O of n. Is that true or not? Already we discussed.
It is true, sir. It
Yes,
is
sir, it is true.
It is true. N power 0.1 is big O of n. Is that true or not? n power 0.1 is big O of n.
True.
True, sir.
N power 0.9 is big O of n. Is that true?
False, sir.
True, no, madam.
True.
See, n
Every
power
amount less
0.2.
than n is true, sir.
Anything less than n, no, it is true only, no.
Not there is 18 to the 36.
N power
Smaller
0.9.
functions are in the order of bigger functions.
That no, this is 1, this
Yes.
is n power 0.9. 1 is smaller than greater than 0.9, no.
Yes, yes, yes.
Even if I take n power, this is n power 1, still it is true or not? True. But we don't know exactly what is its order of graph. We only know that it is between these two. That's why I'm checking for two extremes. If two extremes it is true, means automatically it will be true for any value between that, no? Is that correct? So that means average case also it is true. It is true. Okay. Now, this statement, is it true or not? It is true. It is true. Okay. Now, all of you, most of you must have heard something like this. So it is always better to represent worst case running time of an algorithm using big O. Using big O. This statement, no, all of you must have read in some running. It is always better to represent worst case running time of an algorithm using big O notation. Now, can you tell me why it is true? Why it is true? Why big O notation is preferred for worst case?
Why akka?
Because if this is a worst case, then average case and worst case will always be less than order of n.
Thank you very much. Okay, thank you very much. Yeah. So that means, so
ಇದು ನನ್ನ ಯಾರ ಬ್ರದರ್ ಏನತ್ತನ್ರಿ
okay, I request all the participants to keep your microphone in mute. Okay. Are you what? Worst case running time, why big O notation is preferred? If we represent worst case running time using big O, then it will be true for other two cases also. Is that correct? It will be true for other cases, other two cases also, no? Is that clear?
Sir, clear.
So if we represent worst case running time of an algorithm, here also we represented worst case. Here also we represented worst case. Here first two three we simply represented worst case running time of an algorithm. Okay, using three, all three are correct. All three are correct. Okay. Now in all three statements, I am removing worst case, and we read like this: running time of linear search. This is same. Okay. Next to running time of linear search, big omega of n. Running time of linear search, theta of n. Theta of n. Out of this, which is correct? Only fourth one is correct now. See here, if I remove this and read it, is this true? Running time of linear search is big O of n. Is that true?
Yes, sir.
Yeah. That means if what type of bound big O notation gives?
Upper bound, sir.
Upper bound. It is, if it is upper bound in the worst case, automatically it will be upper bound in best case also, no?
Yes, sir.
Automatically it will be upper bound in average case also.
In both the cases, sir.
That means that's why usually, in textbooks, best worst case running time they represent using which notation? Which notation? Worst case running time, which notation is preferred?
Big O, sir.
Big O.
Big O. What is the reason behind that?
Because it covers worst case and average case also, sir.
Best case and average. Other cases also it is true. In general, it is true. In general, it is true. That means irrespective of case, it is true. But Actually, worst case or best case or average case, which is our favorite notation? Anybody's favorite notation?
Worst case, sir.
Theta, no. What I'm saying is whether best case running time or a worst case running time or average case running time, which notation becomes our favorite? That means we want exact order of growth, no?
Yes, sir.
Which notation is
Theta.
best? Always
Theta
it is
notation.
best. Theta is best. But again, there is a contradiction. No, people say worst case we should prefer big O. With what is the context for which they are saying that statement? In which they are saying that statement? The intention here is if we represent worst case running time using big O, it will be true for other two cases automatically. But
Yes, sir.
no such guarantee is there for big omega and theta. Is
Yes,
that
sir.
correct?
Yes, sir.
That's why worst case big O is preferred. Big O is preferred. Is this statement clear to everyone? Why big O is preferred in worst case?
Yes, sir, it's clear.
Okay, thank you. Now, worst case running time of linear search, if I represent it as big O of n square, is it wrong?
No, sir. It
Case
is
running
not
time
wrong,
of
but
linear
not
search is
precise.
big O of n square. Is it wrong?
Not wrong, sir, but it's not precise.
That is, nobody actually represents like this. Why? Because it is always upper bound. Upper bound should be as small as possible. Then it gives more information about the actual time. Correct?
Yeah, near to actual, sir.
If we want even this one, we can represent it as 2 power n also. Is it wrong? Definition wise, it is not correct. It is correct only. No, it is not wrong. But is it? Anyone represents it something like this? Any textbook they do they write like this?
No, sir.
No, not required. Okay, no, not required. Why? Because there are better bounds here. No, n is better. N is better. But does it mean that it is wrong? No, it is not wrong. But not that much good bound. Good bound. Okay. Similarly, worst case running time, if I write it as big omega of 1, is it wrong? Worst case running time of linear search is big omega of 1. Is that wrong?
No, sir.
No, that is, technically that is correct only. No, according to the definition, is it satisfying? Yes. If I say worst case running time of linear search is big omega of log n, is that correct? Is that correct?
Yes, sir.
Is that correct? Yes. But
Yes, sir.
anybody writes it like that? Worst
No,
case
sir.
running time of linear search is big omega of root n. Is this correct?
Yes, sir.
That is also correct. But what type of bound big omega gives?
Lower bound, sir.
Lower bound. Lower bound value must be always as high as possible. Then it gives more information about actual time. No.
Yes, sir.
Okay. It is again you can remember that example. Corman textbook, cost is greater than or equal to 1 rupee, greater than or equal to 10 rupees. That or cost is less than or equal to 1 crore, less than or equal to 1 lakh, less than or equal to 10,000, something like that. That example, if you remember, all these things will be clear automatically. Okay. It is not wrong, but it's not preferred. That is the meaning. Fortunately, theta, there is no other way other than n. We cannot represent it using any other value, no other value. So finally, worst case running time, why big O is preferred? Worst case running time, why big O notation is preferred?
For best case, worst case, average case.
Other cases also it becomes true.
Yes.
Okay. Now let us see. So among first one, is it true? Now we talk about best case. In the best case, what is its order of growth? Order of growth is
N power to 0, n raised to 0.
n power 0. N power 0 means it is independent of input, no? Input size, no? It is independent of input size. That means it is 1. That means that we call it as actually constant. Whether n is 100 or n is 1000 or n is 1 crore, the value is not going to affect. Okay. It has no impact on that. Now, best case running time of linear search is big O of n. Is that correct?
Yes, sir.
Okay, this is correct. Okay, instead of this, is there any better way of writing this? Is there any better way of writing this? Using
We
big
can
O?
write big O of 1.
This is better, no?
Yes.
So all, let me replace with 1. All are ones. Okay, all are ones. Now you please read and tell me. Okay, best case running time of linear search is big O of 1. Is this true or not?
True,
Yes,
sir.
it is true.
Yes.
It is true. Best case running time, second one, linear search is big omega of 1. Is that
True,
true
sir.
or not?
True, sir.
Best case running time of linear search is theta of 1.
True, sir.
Is that
True.
true?
True.
Okay, true. Now look at fourth statement. Look at fourth statement.
Wrong, sir.
So this becomes true when
All our conditions are
best case running time of linear search is big O of 1. Worst case running time of linear search is big O of 1. Average case running time of linear search is big O of n, big O of 1, sorry. If all are true, then we can say that this answer is correct. This statement is true. Even one among these three, if they are wrong, okay, no, if it is wrong, one among these three is wrong, then we can conclude that this is not correct.
Wrong.
Now you tell me, best case running time of linear search is big O of 1. Is that true or not?
true, sir.
Already the same statement, no, whatever is there, I have written here. Worst case running time of linear search is big O of
Wrong,
1.
sir.
Huh?
Wrong.
This is wrong. Average case, we don't know. Okay, we haven't discussed it, no? We don't know what is the answer. But at least one is false, no? One is
Yes, sir.
false. So from this, what is the conclusion we can draw? This statement is true or false?
False, sir.
It is false. Now, similarly, here, what does it mean? We have three cases now. Worst case running time of linear search is theta of 1. It says best case running time of linear search is theta of 1. Average case running time of linear search is theta of 1. You tell me whether best case running time of linear search is theta of 1. Is this correct? If all
Yes.
three are correct, then sixth statement becomes true. Is this correct? Correct.
Yes, sir.
Okay. Worst case running time of linear search is theta of 1. Is that true?
No.
That means now sixth statement is that true or false?
False.
It is false. Now look at fifth one. Fifth one. Okay. Fifth one. So best case running time of linear search. Running time of linear search is big omega of 1. Next, worst case running time of linear search is big omega of 1. Next, average case running time of linear search is big omega of 1. Okay. Now tell me, out of this, best case running time of linear search is big omega of 1. Is it true or false?
Yes, sir.
worst case running time of linear search is big omega of 1. Is that true or false?
False.
Worst case running time of linear search is big omega of 1. What is order of growth in the worst case? What is order of growth in the worst case?
N.
N.
N. N, that is, N, is it big omega of 1? Is this true or not?
It's true, sir.
It is
True.
true, no? Are you following? You simply go by after getting order of growth, you forget about that algorithm. Okay, only order of growth should be there in our mind. Worst case running time, what is order of growth? Linear search worst case running time order of growth, we know that it is n. It is n. It is n. Now what is that? When does it become true? If n is big omega of 1, it is true. Now is that true or not? N is big
True.
omega of 1. Is
True,
that
sir.
true or not?
True, sir.
It is true. So average case running time of linear search is big omega of 1. In the average case, what is the value? It may be from n power 0 to n power 1. Anything in this range, big omega of 1 is true or not?
True, sir.
Any
Ah,
value, n
no,
power
no.
0 also big omega
False.
of 1 is
False.
no. See, n power 0 is big omega of 1. Is this true or not? N power 0.1 is big omega of 1. Is that true or not? N power 0.2 is big omega of 1. Is that true or not? And swan n power 0.9 is big omega of 1. Is that true or not? N power 1
Yes,
is big
yes. True, sir. True.
Are there any wrong answers here?
No,
All
no.
are true, no?
Yes, sir.
That means average case running time of linear search is big omega of 1. Is it true or not?
Yes, sir.
Yes. So now you tell me out of this fifth one, is it true or not?
Yes, true, sir.
True. Now, okay, you must have read in textbooks, no? Always it is better to represent best case running time using big omega notation.
Mhm.
Can you-
Yes, sir.
Yes. So why? What is the intention? What is the intention? If the best case running time is represented using big omega,
Mm.
it will be true for other two cases also. No, it will be true for worst case also. It will be true for average case also. No. In general, best case running time minimum. See, big omega notation gives what type of bound?
Lower bound.
Lower bound. So best case running time means minimum number of operations performed. For minimum
Yes, sir.
number of operations itself, it is lower bound.
Yes, sir.
For maximum number of operations, whether it becomes lower bound or not,
Yes.
that no.
Yes, sir.
Similarly, for average number of operations will be definitely greater than or equal to minimum number of operations. Even
Yes, sir.
worst case, maximum number of operations will be greater than or equal to minimum number of operations. Hence,
Yes.
best case running time is represented using big omega notation. It will be true for other two cases also. That's why big omega is preferred in best case. The reason is that. But any case, whether it is best case or worst case, what is our favorite notation?
Big O.
No. Theta notation. See, again, simply remember cost of the book. Okay, no, that example. If you ask someone what is cost of the book, if they clearly say that is 400 rupees, that answer is better, or less than or equal 400, that answer is better, or greater than or equal 400, that answer is better, provided all three are correct.
Exact price.
Exact answer is better, no? Like that,
Yes.
for best case also theta, if they represent, that is very good, no? It gives
Yes.
more information about actual best case running time. But why
Okay.
people say that big omega is preferred?
It is, it gives
Other
minimum
two
number of,
cases also it gives bound. Other two cases also it gives bound. Is that clear or any doubt? O- Okay, let me write some statements. I'll ask you true or false, then we'll move on to next. Average case running time of linear search. Okay. Running time.
sir, one doubt, sir.
Please tell me, madam.
Some books says that best case you better use big omega, worst case is big O.
Correct, madam.
And the average case with the theta. No, is that
Always
true
theta
or
is
not,
best.
sir?
But the reason that's what I said, no, man. Best case if we use omega, why
Mm.
what is the additional information it gives? The same answer becomes true for worst case also. It is also true for average case also. That's what no here. See, you read this statement like this. Running time of linear search is big O of 1. Is it true? Is it true?
Running time of linear search is big of 1. No, sir.
It is false, no? But here
Mm.
you remove this and read.
Which one, sir?
Second one.
Best case running time of linear
No,
search.
best case you should not read it.
Mm. Running time of running time of linear search is big omega of 1. Yes, it.
That means
Yeah.
say best case if I use big omega, then it will be true for in general 3 cases also. No, that is the meaning, no?
Yes, sir. That
So that's
means
why-
for all the cases, it is the lower bound.
It is lower bound. That's what, madam. Final point. Similarly, worst case, no, previous slide. Worst case. So which notation is preferred?
For worst case, big O.
Big O. That's see. You second statement. You please read. Worst case running time of linear search is big omega of n. It is correct, no?
Yes, sir.
Now you read without worst case. Running time of linear search is big omega of n. Is that correct?
Running time. That means minimum n comparisons.
No, it is not correct.
It may not be true for all these situations. It is not always n.
Madam, only we have true or false answers, madam. May not be true means it is false only, no?
Yes, sir.
That's all. So that means worst case running time, if I represent using big omega, it is not true for there is no guarantee that it is true for other 2 cases. But here you please read the first statement without worst case.
Running time of linear searches.
Running time of linear searches, is it true for best case?
Yes, sir.
All cases it is true, no? Because it is
That
upper
means
bound.
upper bound.
For worst case, automatically it will be upper bound for best case also. It will be upper bound for average case also. That's why worst case big O is preferred. Is it clear, madam?
Yes. So people, I mean, అందరు ఏమనుకుంటారంటే worst case అంటే, I mean, big O is in the worst case, it should be n, but it must be true for the other cases also. That many people doesn't know, sir.
Only confusion. No, people think that worst case always I should represent using big O of n.
Yes.
Using big O notation.
Yes, sir.
That is not the point. No. If you represent what is the additional information it gives is this is the additional information. That's why it is preferred. But actually, worst case, if we write it as theta of n, that is best answer. No. Why confusion? If I know that cost is 500 rupees, why should I intentionally give answer as less than or equal 500, madam?
Yes, sir. Yes.
I'll simply say it is 500. That is theta of n close, no?
Mm-hmm. Mm. So then we can, shall we say that for linear search, running time is theta of n, worst case is theta of n is true.
That is true, madam. That is true. Our third statement,
Mm-hmm.
third statement is that only, no, madam.
Okay.
Worst case running time of linear search is theta of n. That is correct, no?
That means that it won't go beyond n.
What is, because worst
It
case
is exactly.
worst case order of growth is n, no? That we know. First, we need to calculate order of growth, madam. After calculating order of growth, it is simply definitions of asymptotic notations, no? This have no role, no. Once n power 0 is known, n power 1 is known. After that, this is only asymptotic notation definitions, no.
Yes, sir. Yes.
We can even forget about this entire thing. Only we can assume here n power 1 is there. That's all. Okay. Is it clear to everyone why big O is preferred in worst case, big omega is preferred in best case?
Yes, sir.
Okay, thank you. Okay. Now we move on to the other case, remaining case in linear search. What is that? Average case running time of linear search. So
Sir,
for that,
shall we assume that if any algorithm time complexity is with the theta notation, that's the best algorithm?
that means if we do proper analysis, then only we will be able to exactly calculate its order of growth. No, simple algorithms, it is very easy to find out what is its order of growth. Later we'll understand that for some difficult algorithms, no, estimating its order of growth itself, it is very difficult task. Analyzing, that means what is finding order of growth of running time, no, it is difficult. That's why easy part is you can say that exact mark is, we don't know, maybe 30 or 40 you get. We, instead of saying why 30, 40, saying I will say my mark is not more than 100 out of 100. That is easy answer, no, madam.
Yes, sir. Yes.
That will be true, no, whether you get 30 or 31, 40, even more than 40 also, your answer is true, no.
Okay, okay.
But that 100 answer is easy to give, no.
Yes, sir.
Even if you want to give even better, you may, if you are confident, then you might say it is less than or equal 60 instead of saying less than or equal to 100.
Okay. Now, my doubt is if we give theta analysis,
Yes,
the
ma'am.
analysis is done perfectly or the algorithm is good?
No,
Which
algorithm. See, notations and algorithm, there is no relation at all. Only that is our convenience, no, because I have done everything. After doing everything, I will say that what best case. Okay, say for example, worst case running time of linear search is big O of n factorial. Is this true? I know that its order of growth is n, but still I have written as big O of n factorial. Is that true?
No.
Is that true or not? Worst case running time of linear search is big O of n factorial. Is that true or not?
True, sir. True.
True only, because you should not, the moment it is asked to know what is that which should come to our mind, what is its order of growth? Order of growth is n power 1. After that, what is that? Only simply we are checking whether it is true or not. No, that's all, no, madam.
Yes,
It is
sir.
true only. Even if we are right, it is worst case running time of linear search is big O of n power n. Is this true? That is also true, no, madam.
That's true. True, sir. సరే ఇంకొకటి ఇప్పుడు ఒక బ్యాడ్ అల్గోరిథం ఉంది ఐ మీన్ లెట్ us say some bad algorithm for that some person is giving theta notation, theta analysis.
Theta means first that any whether it is good algorithm or bad algorithm, we can represent it using big O also, big omega also, theta also. These notations, they don't
Describe the algorithm quality.
It is nowhere relevant, no.
Yes, sir. Yes. Yeah.
Only that first initially we discussed, whichever algorithm's running time has a lower order of growth, that algorithm is efficient or good, madam. That's all. These notations, they don't have any role in that, no.
Okay. Yes.
Only one point is whichever algorithm's order of running times order of growth is lowest, that is best algorithm. That's all.
Okay. Okay. Okay, sir. Thank you.
Okay, okay. Next, we will calculate what is the average case running time of linear search. For that, in average case, we need to assume something about the distribution of input. For that, whatever is basic terminology and required, no, that I will discuss first. First, all of us know what is a random process. What is a random process? Can you give me an example for random process, random experiment or event?
Of a coin.
Tossing a
Coin
coin.
is toss. Yeah.
Tossing a coin, it is a random experiment, no?
Yeah.
Okay.
Throwing a dice.
Throwing a die, picking a card from deck of 52 cards. These are all experiments, no, random experiments, okay, no, events. Now, what is a random variable? Okay, informally, more informally. Okay, what's a random variable? What's a random variable?
It can take any value from the given range, within the given range.
That means, for example, throwing a die. What can you give me a random variable in that experiment? We are throwing a
Yes, sir.
die. What is random variable?
3. Yeah. From 1 to 6, it can get any value, maybe 3, 4, 5, 1.
Oh, that means if you throw a die, so for example, 6-face die, I'm assuming, okay, 6-face die. So what are the values we get? Outcomes, it may be 1, or it may be 2, or it may be 3, or it can go up to 6. So these are the values of this experiment, no? This, our random variables, we don't know which value we get, whether 1 we get, or whether 2 we get, or 3 we get, or 4, okay? We get, or 5 we get, or 6 we get. Similarly, I am throwing 2 dice at a time. Now, can you tell me what is a random variable here? Or what are the outcomes here when we throw 2 dice simultaneously? What are the outcomes?
Could be 1, 1, 1, 2, 1, 3.
1, 1, 1, 2, 1, 3, 1, 6, 2, 1, 2, 2, 2, 6, 3, 1, 2, 3, 6, 4, 1, 2, 4, 6, 5, 1, 2, 5, 6, 6, 1, 2, 6, 6. That means 36 outcomes we have now. 36 outcomes we have. Now, can you define a random variable in this event, in this experiment?
Anything that takes from 2 to
What can you define a random variable in this case?
So
The variable whose outcome
has
is
to-
not.
No, I am asking for an example. So my experiment is, okay, throwing, say, 4 dice. You define a random variable. You tell me what is that we can consider it as a random variable in this case. 4 dice I am throwing at a time.
Sir, I
the
think
sum of the numbers on all the dice.
That is number of ones which I get. No, that I can consider it as random variable or not.
Yes, sir.
Number of ones in all dice. And the number of ones can be minimum 0, maximum. It can go up to 4. And whether it is 0 or 1 or 2 or 3 or 4, it depends on only outcomes, no, of this 4 dice. First die, it may be 1 to 6, anything we get. Second die, we get 1 to 6. Third die, 1 to 6. Fourth die also 1 to 6. This value depends on outcomes or not. Experiment outcomes. Now, tossing a coin. Can you define a random variable in this case?
Head and tails.
No, random variable. What is our random variable?
yes, sir. 0 or 1.
No. What is random
The
variable?
number
Means
of
it
tiles.
is a variable whose value we don't know exactly. It may.
The number of heads or number of tiles.
Thank you very much, sir. Okay, no, sir. That is, we can say what is number of heads. Let X is number of heads. then what are the values X can take?
1 or 2.
No, 0 or 1, no?
Ah, yes, sir. 0 or 1.
One coin I am tossing, fair coin. Okay, no, 0 or 1.
Yes, sir. Yes, sir.
What is the meaning of random variable? Is it clear? Is there any doubt? Okay, that you can read also further. What's a discrete random variable? Now, whatever examples we discuss, what any random variable, number of heads or number of ones after throwing 4 dice, okay? All this, what is the value it takes random variable? 0, 1, 2, 3, 4, or 0, 1, all are what type of values? What type of values?
Discrete values.
Distinct values. No, clearly they are separated. No, distinct separated values. No, there is 1 is different and 2 is different. Between 1 and 2, are there any other valid values? No.
No.
Okay. Are you getting this type of values? No, discrete value. A random variable which assumes this discrete values. No, that we call which takes discrete values, that we call it as discrete random variable. Okay. Now, for example, X is a random variable. X is a random variable. X is a random variable. So we are tossing a coin. This is a coin, tossing a coin. Okay. Tossing a coin, say. Okay. Tossing a coin. Now here, what are the random variable associated with getting number? It is also with the number of heads. Number of heads. What is number of heads? Number of heads. Instead of 1 coin sale, we are tossing 2 coins. And let us take 3. What is number of heads? 0, 1, 2, or 3. I am tossing 3 coins. All 3 coins I may get a tail. Okay. Or in that case, number of heads is 0. Otherwise, it can be 1, it can be 2, or it can be 3. That means it is a discrete random variable or not? It's a discrete random variable or not? It's a discrete random variable or not?
Yes, sir.
Yes. Now, there is a probability associated with this is X. X is a random variable. I can assume it as X taking value. This is X1 value. This is X2, X3, X4. That means X can take values like X1, X2, X3, X4. In general, we can say X can take values X1, X2, X3, and this one say Xn. Next, we can talk about what is the probability. We don't know which value X takes. Then we can ask what is the probability with which X takes value X1. That means we can ask what is P of X1. What is the probability with which X takes value X1? We can talk about that now. Similarly, what is the probability with which X takes value X2? Similarly, we can talk about what is the probability with which X takes value Xn. Is that correct? Is that correct? Now this details also, this also we can calculate. No, for each value, see, you please read this. Discrete random variable is list of probabilities associated with each of its possible values. That means possible values are X1, X2, Xn. What are the corresponding probabilities? List of probabilities?
P of
X1, P of X2, P of Xn. Okay, no? P of X1. Is that okay?
Yes, sir.
So we call it as probability mass function. Usually discrete case. In continuous case, usually probability density function. No. Okay, you please try
Small
to.
doubt, sir.
Please tell me, sir.
Sir, in point 2, random variable is defined, and point 3, discrete random variable is defined.
Yeah.
Are both different or same, sir?
No. We have continuous random variables also. No, they take continuous.
Okay, sir.
values.
Okay, sir. Okay, sir. Thank you.
But we confine our discussion. We require only discrete random variable here for our analysis of linear search. That's why I defined only discrete random variable. That is the
Okay, sir. Okay, sir. Thank you.
Okay. Next. See, in the best case, what happens? For example, if we have only discussed linear search, in best case, it says that among all possible inputs, if a key is present in first position, that is best case, no? Key is present in first position, it is best case. Okay. Now there are so many cases where key is not present in first position, no? Our algorithm, does it say anything about if a key is not present in first position, how many times that a comparison operation is performed? Does it say? See, best case means that is only special case. No, key is present in first position. Okay, other than that, key is not present in first position. Best case, is it going to say anything about actual number of comparisons performed in that case? General case where key is not say present in first position.
No, sir.
No. Similarly, worst case, what does it say? It is other extreme. Other extreme. Okay, if answer, okay, in maximum, how many comparisons are performed? It says no. That is also one extreme, no. That is also an extreme. That means key should be present in the last position, or key should not be present in the array at all, no. That is worst case, no. But intermediate cases, is it going to address either whether this best case or worst case? Are they going to say something about general cases? They talk about two extremes, no. They talk about two extremes. In general, how does it behave? They don't say anything about it, no. Is that okay? So that's why, in general, how does our algorithm behave? In order to understand that, we go for actually average case analysis of our algorithm. Okay, no, average case analysis or average case running time of algorithm. But in order to do average case analysis, we need to understand something about distribution of our input. What type of input we get, values we get as input. What type of values we get as input, that we need to understand. Okay, that we need to understand. So for that, what we do know, we actually make some assumptions about, okay, assume that I get this type of input. Assume that we get this type of input. Like that, some assumptions we make. And usually what type of assumptions we make? No standard assumption that we make is, we assume that it is simple uniform distribution. Simple uniform distribution. So in case of linear search, n is input size. Keys, there are n, array contains n elements, 1, 2, 3, like this, nth position, 1, 2, 3. Okay, this is array. So what does simple uniform distribution mean? So in general, key may be present in this position, or key may be in first position, or key may be in second position, or key may be in third position, or it may be in nth position. No, we don't know which position it is in. Possibilities are, it may be in first position, or it may be in second position, it may be in third position, it may be in nth position. Okay, but my input, no, most of the time I get input in such a way that my key is always towards starting only. Either it may be first position, second position, or third position. Or I may always get input where my key I am looking for, no, it may be present in, it is most likely that it is present in only last 3 positions. That means towards end. These are some possible input cases, no? We always may get input where my key is present towards starting. We always may get input where our key is present towards the end. These are the possibilities, no? It depends on what type of data we get, no? Are you following this?
Yes, sir.
Okay, so, but we don't know what type of data we get. That's why we make this assumption. So you please read, what does it mean? It refers to a type of probability distribution in which all outcomes are equally likely. That means here you tell me if I assume that it is simple uniform distribution, what does it say? What does it say? All
The assumption that the element is in first position, or in the second position, or in the third position, and so on.
No. If I assume that whatever input I get, it follows simple uniform distribution. That means, what does it mean? What does it mean? What does it mean? Whatever be the chance that key is present in first position, same thing is the chance that it is present in second position, same thing is the chance that it is present in third position, and so on. Same thing is the chance that it is present in nth position. No, we have how many options per key? It may be first position or second position or third position or nth position. N different options we have got. No, out of that, which are our favorite answers, favorite positions where key is okay? Now there is a high chance that key is present towards starting only, or there is high chance that key is present towards ending only. We are not assuming like that. We are saying whatever chance is probability or chance that it is present in first position, same thing is the probability that it is present in second position, same thing is the probability that it is present in third position, and so on. Same thing is the probability that it is present in nth position. Now you tell me, what is the probability that it is present in first position?
1 by n, sir.
One by
Because
n.
all are equally likely, no? 1 by n. What is the probability that it is present in? What is definition of probability? Favorable number of outcomes by total number of
Total.
outcomes. No? I am looking for first position. That means this is my favorite position. Favorite position. That means how many positions are in our favor? One position. Total how many I have? Total how many I
N.
have?
N.
Yes.
Okay. If key is always, what is the probability that key is present in second position? What is the
One.
probability that key is present in second position?
1
Same,
by
sir.
n.
1
1
by
by
n.
One, not 2 by n. It is only one
1 by n
position. No. Oh, I have n positions. Out of that, it is one position. So it is again 1 by n. What is the probability that it is present in nth position?
1 by n.
It is also 1 by n. Is that okay? Okay. If I toss a fair coin, what is that we get? A coin means we have heads and tails. No. What is the probability of getting head? I have two possibilities. No, two outcomes we have. You tell me if it is simple. Fair coin means both have same equally like, no, both options are equally likely. No, then what is the probability of getting head? What is the probability of getting head?
1 by 2.
What is the probability of getting tail?
1
1
by
by
2.
1 by 2. Because out of 2, 1 is in our favor. Is the difference clear? What does simple
Yes, sir.
uniform distribution? No, there is no biasing. All positions are same. All positions are equally likely. All positions are equally likely.
Mm.
Okay. So in that case, what does discrete uniform distribution mean? Whatever we have, all outcomes are discrete. They are distinct separated values and have same probability. In that case, whatever we discussed, no probability of head. If a fair coin means head is same as tail. No. Similarly, probability that key is present in first position 1 by n, key is present in second position 1 by n, third position 1 by n. That is discrete. Is that correct? Is that correct? Rolling a die. If you roll a die, what is the probability of getting 1 under simple uniform distribution?
1 by 6.
1 by 6. Getting 6. What is the probability of getting 6?
Also 1 by 6.
5 also 1 by 6. If choosing a card from deck of 52 cards. 52 cards. No, what is the probability of getting specific card?
1 by 52.
1 by 52. Whatever. Okay. Now in this case, what is the probability of any outcome? It is 1 by total number of different values. Outcome. How many different values are there in that? That's why, no, in case of that linear search, no, we got 1 by n. 1 by n. Now we know that, okay, last 2 minutes I close so that linear search will be complete. X is a random variable which takes values x1, x2, and so on, xn. there is a probability associated with it. P of x1, this is, okay, or simply I can write it as P1, this is P2, and so on, this is Pn. Then what is expectation of x? What type of random variable it is? X1, x2 are different values, no? That means what type of random variable it is? What type of random variable it is? Discrete random variable. Then what is expectation of x? What is expectation of x? What is expectation of x? What is if x is a discrete random variable with values x1, x2, xn and associated probabilities p1, p2, pn, what is expectation of x?
xi into pi of x.
Xi into pi, that is x1 into p1 plus x2 into p2 plus xn into pn. Okay, that's what it says. Okay, now a discrete random variable means number of possibilities. No, we have different values, but that is countable. Okay, no, countable. Probability is always between 0 and 1. Sum of all probabilities is always 1. Okay, now last minute. Now, what is expected running time of linear search? Expected running time of linear search. So we assume that it is simple uniform distribution. We have n keys, input size is n. We assume that it is simple uniform distribution. Simple uniform distribution. That means what is the number of comparisons that is performed in this case? What is number of comparisons it is that is performed? It can be 1 or it can be 2. If it is in this position, number of comparisons is 2. If key is in this position, third position, it is 3. So number of comparisons varies from 1 to n. Now you tell me what is the probability that key is present in position 1? If I assume that it is simple uniform distribution,
1 by n.
1 by n. With the assumption that key is present in first 1 to, I assume that always key is definitely present. That means search is successful. Always search is successful, but we don't know which position it is present. That is not clear to us. Which position it is present is not clear, but we know that it is successful. Then what is the probability that it is present in second position?
Also 1 by n.
1 by n. Third position 1 by n. Ith position 1 by n. Nth position also 1 by n. Then what is expectation of x? Sigma pi xi 1 into 1 by n plus 2 into 1 by 1 into 1 2 into 1 by n plus and so on plus n into 1 by n. Okay, 1 by n we can take common, then it will be 1 plus 2 plus and so on plus n. What is sum of first n natural numbers? N into n plus 1 by 2 is the formula. So finally, what is that we get? What is that we get? N gets cancelled, n plus 1 by 2. So now what is expectation of x? What is expectation of x? N plus 1 by 2. This is expected running time of linear search. What is its order of growth? What is its order of growth? It is 1 by 2 into n plus 1 by 2, no? What is its order of growth? What is order of growth?
N.
N. So therefore, what is average expected or we also call it as average case. Why? Because we assume this as simple uniform distribution. All positions are equally likely. What is average of 8, 9, and 10?
9.
9, no? So this, that means I am giving equal weightage to each one, no? Then I am taking 8 into 1 by 3 plus 9 into 1 by 3 plus 10 into 1 by 3. Then it is equal to 9. 8 into 1 by 3 plus 9 into 1 by 3 plus 10 into 1 by 3. It is equal to 9 or not? That means if probability is no, if you give equal probability for all, that means simple uniform distribution like this, then average and expectation both are same. Average and expectation both are same. Now what is average case running time of linear search? Linear search order of growth is n. Can we write it as theta of n? Can we write it as big omega of n? Can we write it as big O of n? Is that okay?
Sir,
Okay, I just stopped here. Okay, if you have